Namaskar, welcome to the channel Anka Anand Aharan. That is, let us extract happiness from the teaching learning process of mathematics. In this channel, we have discussed about different varieties of subjects, out of which one of the subject is measure theory, and this is third video in related to measure theory. Today we will discuss some of the properties of a measurable set. One of the property is excision property. Let A be a measurable set of finite measure which is contained in B, then outer measure of B difference A is equal to outer measure of B minus outer measure of A. Let us prove it. So what is given here? A is a measurable set such that outer measure of A is finite. And B is containing A, or A is a subset of B. Now diagrammically how it will look? It is my B, it is my A, this is B, this is A, and this portion, in between portions are, these elements are B difference A. Now here what we are observing, as A is a subset of B, what about B intersection A? It is nothing but A. Similarly, what about B intersection A complement? This is nothing but A complement intersection B. That means these portions, these common portions. That is, it is nothing but B difference A. So now given is A is measurable. We have, since A is measurable, so for any set B, what we are having? Outer measure of B is equal to outer measure of B intersection A plus outer measure of B intersection A complement. So out of which, what is B intersection A? It is nothing but A. So this is equal to outer measure of A plus outer measure of B intersection A complement, which is outer measure of B difference A. This step. Now from this step, as this outer measure is finite, I can take this value to that side. So how much we are getting? Outer measure of B difference A is equal to outer measure of B minus outer measure of A. What is the reason behind it? I can do it because the outer measure of A is a finite value. Hence this result is proved. Now let us prove a theorem. This theorem is giving us several equivalent conditions that a set E satisfies when it is measurable. If E is any measurable set, then it is equivalent to say that E is measurable. It is equivalent to say that for each epsilon greater than 0, there exists an open set O containing E such that m star of O difference E is less than epsilon. Diagrammically, how it is? If this is my E, E is given as measurable. So as out of that means this value is with me. And for every measurable set E, there exists a there exists a set O, open set O. This is open set O, and this is my set E. So in between, what is the difference? This portion is the difference. What is this portion? So it is O difference E, this portion. So this portion, there exists O such that for every epsilon, this is less than epsilon. That means what? For every epsilon, there exists, this is less than epsilon. That means I can get a set O as close to E as I wish from outer side. So now this condition is to be proved as same equivalent to Another condition, condition 2, what it is telling? There is a G delta set G containing E such that this outer measure of G difference E is equal to 0. So what is a G delta set? G delta set is countable intersection of open sets. Open sets, I have countable number of open sets. Their intersection gives me a G delta type set, which is measurable according to an old result already discussed. Now, similarly, if this is equivalent to that, not only an open set exists from the outer side. Similarly, for each epsilon greater than 0, there exists a closed set F contained in E such that m star of E difference F is less than epsilon. Again, in a similar version, there is a F sigma set F contained in E such that outer measure of E difference F is 0, out of which the first two we will prove, which is coming with the equivalence of the measurability of E, and then from the second result we will get E is measurable, and ultimately using the De Morgan's law, that is union complement of union is intersection of their complements. Similarly, open sets complement is closed and closed sets complement is open, and E is measurable implies complement of E is measurable. So with these conditions we can prove the last two results. So now we will start with the concept that E is measurable. We are claiming that there exists an open set O for every epsilon greater than 0 such that outer measure of O difference E is less than epsilon. We want to prove this. This is our target. So before going for it, we will break the result into two cases. This E can be a measure of finite measurable set of finite measure, finite outer measure, or it can be of infinity outer measure. First, let us assume E is of finite outer measure. That is, outer measure of E is finite. Now, for every epsilon greater than 0, from the definition of outer measure, what is outer measure? Outer measure of a set is the infimum of the collection of the open intervals which covers countable infimum of the sum of the length of the collection of countable collection of open intervals which contains E as a subset or which covers E. Then from the definition of this, what we are getting? It is for every epsilon greater than 0, there exists a collection such that E is a subset of union of Ik. What is Ik? Ik is a countable collection of open interval. And such that the union contains E as a subset of it. Now, not only this, this also satisfies this according to the definition of infimum. Infimum plus epsilon will be always less than one of the element of the set. So that's why there always exists a collection, countable collection of open intervals such that this condition is satisfied. Okay, that is sum of their length is less equal to outer measure of E plus epsilon. Now, what is our target? Our target is to find out O. Let O is equal to union of all these open intervals. As we know that open intervals are open sets and countable union of open sets is always open. So O is an open set and O contains E as a subset of it. Now what is outer measure? So that implies outer measure of O is less equal to this length, because this length infimum gives me outer measure of O. So naturally this length is always greater or equal to outer measure of O. But this length is less than outer measure of E plus epsilon. Now what does it imply? It implies outer measure of O minus outer measure of E is less than epsilon. Just now we have discussed in the above result, that is the excision property. It tells us that as E is a measurable set of finite measure, so outer measure of O difference E is less than this value, whatever value we are having here, this is equal to this. Hence, outer measure of O difference E is nothing but outer measure of O minus outer measure of E. Hence, we got this is less than epsilon. Let us assume it as condition 1. Now, let us take the outer measure of E is infinity. Again, we know that every measurable set, in fact, every set of real numbers can be expressed as a disjoint union of measurable sets of a finite measure. So every measurable set can be expressed as a countable collection of disjoint measurable sets of finite measure, such that E is equal to union of k is equal to 1 to infinity ek. Now ek is a measurable set with finite measure. So that implies, for just now in A we have proved that if any set is measurable with finite measure, then there exists an open set OK which contains ek such that the outer measure of OK difference ek is less than epsilon k for each epsilon k greater than 0. So here what is our epsilon k? Our epsilon k is nothing but epsilon by 2 to the power k. Epsilon which we have considered in part 1. Epsilon by 2 to the power k. Now collecting all such open sets union as O. What is O? O is nothing but union of k is equal to 1 to infinity OK. Clearly O is an open set. And E is contained in O. So now what is O? O difference E is a subset of, this is a subset of, in place of O I have substituted the value what it is? It is k is equal to 1 to infinity OK difference E. Now let us observe the diagram. So what is my Ek? Ek is a disjoint collection of measurable sets. So what I have done, so E is broken into several pieces, E1, E2, E3 and so on, Ek and so on. So there are countable collections and each one is disjoint from each other and their union is E. Observe this diagram. So for E1, which is a finite measure, there exists O1 containing E1. Similarly, for E2, there exists O2 containing E2 as a subset. So likewise, for every set Ek, there exists an OK, such that Ek is a subset of OK. And outer measure of OK minus Ek is less than epsilon by 2 to the power k. So with this condition, let us discuss further. Observe the diagram. I hope it is understood. So now what we are getting? O difference E is in here. I have substituted the value of O. Then we have taken k is equal to 1 to infinity OK, which is nothing but this collection is a subset of OK difference Ek, their union. So naturally outer measure of this is less than outer measure of this collection, and this collection each one is a disjoint set. So this is always length of, we know, according to countably subadditivity property, outer measure of union, countable union of sets is less equal to sum of the outer measure of the set. So according to that, this condition holds true. Now, each outer measure m star of OK minus EK, what is its value? Its value is E by 2 to the power K, for in which the sum over ranges from K is equal to 1 to infinity. Whatever its value, we know that it is A by 1 minus R. So here A is epsilon and 1 minus R is A is epsilon by 2 and 1 minus R. R is half. So epsilon by 2 by half, it is nothing but epsilon. So here we got this result. So finally what we have observed, outer measure of O difference E is less than epsilon. So this we have done for infinite outer measure, and previously in A part we have done for finite outer measure. That is, for any measurable set we will always get an open set O such that O contains E and outer measure of O difference E is less than epsilon. That means we can always come closer to E, as close to E as we wish, so that the difference is of measure, outer measure, 0, almost. Less than epsilon means almost 0. So from 1 and 2, for every epsilon greater than 0, there exists an open set O such that E is a subset of O and outer measure of O difference E is less than epsilon. That is, this E is measurable implies first condition I is obtained or I holds true. So we have got one part done. Now I implies the first condition implies the second condition. So what is the first condition? First condition is telling us that for every epsilon greater than 0, for every epsilon greater than 0, there exists O such that E is contained in O, open set O, and outer measure of E is contained in O, and outer measure of E is nothing, outer measure of O difference E is nothing but it is less than epsilon. This condition is with us, and with this condition we will go for this second condition. What is the second condition? That is, for every measurable set E, we will always get a G delta set small capital G such that G contains E as a subset of E and G difference E is having outer measure 0. This is our target. So to prove it, we know that for each natural number K, let us fix E is equal to epsilon is equal to 1 by K. Then for every epsilon greater than 0, 1 by K is always greater than 0. And for E, we have an open set OK such that E is a subset of OK and outer measure of OK difference E is less than 1 by K. So always for every E we will have, and for every epsilon 1 by is equal to 1 by K we will get such OK. So collect all such countable open sets OK and take their intersection to get G. Naturally, G is an open set. G is a set which is obtained from the countable intersection of open sets. That is, G is a G delta set. And as E is a subset of OK for every K, naturally E is a subset of their intersection. That is, E is a subset of G. Now, E is a subset of G and G difference E is a subset of OK difference E. So according to the monotonicity property of outer measure, we get m star of G difference E is less equal to m star of OK difference E, which is strictly less than 1 by K. So this implies that this value is always non-negative and it is less than 1 by K for every natural number K. That implies it is less equal to 0 and greater equal to 0. That implies it is equal to 0. Hence it is proved. So what we got here, G is a countable intersection of open sets. Hence G is a G delta set. That means we got a G delta set such that E contained in G and outer measure of G difference E is equal to 0. Hence 1 implies 2 is proved. Similarly, by applying the De Morgan's law and E measurable implies and implied by complement of E is measurable, we can prove that 1 implies 3 and E is measurable implies E complement is measurable. So as E complement is measurable for every epsilon greater than 0, there exists open set O such that E complement is contained in O and m star of O difference E complement is less than epsilon. Here what we have done? In place of E, we have substituted E complement, nothing else. E is measurable implies E complement is measurable. Now, what is O? O is an open set which contains E complement. What about O complement? O complement will always be a closed set. So, let O complement is equal to F. So, F is a closed set. So, clearly this implies F is a closed set. Closed set. So E complement is a subset of O implies and implied by O complement is a subset of E, which implies and implied by F is a subset of E. Now observe the diagram. The inside structure is E complement and the outside circle like structure is my O. So what about O complement? The portion which is belonging to the region outside O, that is my F. And what is E complement's complement, that is E, that is this portion. E complement onwards, outer side, everything is my E. Okay, so what about E difference F? Observe, E difference F is nothing but O difference E complement. This is our observation. We will go for our result now. What it is telling us? It is telling us that O difference E complement is equal to E difference F. So which implies outer measure of E difference F is equal to outer measure of O difference E, which is less than epsilon. Hence, since O is open if and only if F is closed because they are complement of each other. That is, we got a closed set F contained in E such that outer measure of E difference F is less than epsilon. So we have proved here, this is both side implies and implied by. So 1 is implying and implied by 3. Similarly, we can take 2 implies and implied by 4 by applying De Morgan's law and open set complement is closed, closed sets complement is open, and E is measurable implies and implied by E complement is measurable. So now one part is left that one of these 4 conditions imply E is measurable. Now let us take 2 is satisfied. Let us prove E is a measurable set. Let second condition holds true. That implies what? There exists G such that E is a subset of G with outer measure of G difference E is equal to 0. We know that for any set, this G is nothing but it is a G delta set. Okay, we know any set of outer measure 0 is measurable. So this is a set. What about the set? This set is of outer measure 0. So this set is measurable. And every G delta set which is G is a G delta set and every G delta set is measurable. Hence, what we are getting, this is the result which is given. It is from the book. It is presented here. The collection M of measurable sets is a sigma algebra that contains the sigma algebra of Borel sets. That's why each interval, each open set, each closed set, and G delta set, F sigma set is measurable. G delta set is a set which is obtained from the countable intersection of open sets. F sigma is a set which is obtained from the countable union of closed sets. So already from this result, G delta is measurable and any set which is of outer measure 0 is measurable. So this set is measurable and G is measurable, which implies this is measurable, this is measurable. This is measurable means its complement is also measurable. Whole complement, that is also measurable because this whole is a measurable set and this is a measurable set. Intersection of two measurable set is again measurable. Hence, E is measurable. So this is proved. Finally, what are the things we have proved? E measurable implies I implies second question. First condition. E is measurable implies first condition implies second condition, and second condition implies E is measurable. Second condition implies and implied by third condition implies and implied by fourth condition. Hence, this implies that all the results are equivalent. That is, equivalence of all the conditions is proved. What it is? That is measurable implies and implied by all the four conditions. With this, we will conclude our today's video. Next class, we will discuss about some more things.